Hi, welcome to the Calculus 1 lecture series. And this is lecture number 5. And in the units, limits and derivatives. All right, so for this lecture, we're going to take a look when the x approach to infinity for a function and what could happen to the limits here. Okay, so let's go ahead, go to our lecture notes here. Okay, so if you kind of remember for our previous lecture, we talk about the limits, right? So we say the limit x approach to a f of x is here, and we say what is the limit of that, right? So now, so the a, like in here, that's what we did before. So the a is a constant. And now we said, how about instead of go to the a, now the x approach to the infinity. That means, like the x, so here we want to see what is the limit x approach to infinity here. So the way we defined is like this. We said the limit x approach to infinity. Of course, you can do the negative infinity as well, right? So you have two ends. So because this is our coordinate systems here, right? Okay, so for this coordinate systems here, then the x can go to the positive infinity or x could go to the negative infinities, right? Okay, so we said the limit f of x approaching to infinity, f of x is equal to some values here. That means when the x going to the bigger and the bigger values, and then, the function going to approximate, we're getting closer and closer to some fixed number. So let me try to graph it. Maybe you will have a better idea here. So here, okay. So let's see here. So if I have a function, I go this way, all right? So I go this way. This is, I call this is y. This is equal to the f of x functions here. And now, okay, so now you see when when the f of x go infinity, and then this line is getting closer and closer to this line. So you will get very close to this line. This line is at the value of the L, but it will never touch this line. See here. That's why we said this is the limits at infinity. So when the x go to the infinities here, right? Of course, you can have so sometimes, when the limit, okay, so like x approach to infinity, f of x is here, you don't have to approach to certain numbers. So how about if this approach to infinity? What's that means here? That means, let me have a pictures for you also. So that means in here, okay, so if I have, this is my functions, right? So if this is my f of x function, so as you can see, when the x continue getting bigger and bigger, so what is my y values here? My y value will become bigger and bigger, right? So when the limit x approach to the infinities here, you could either approach to a fixed number, or you could approach to some infinity as well. Like I said, I used the positive infinity as the example, and then it's true for the negative infinities as well, all right? Okay, so now let's take a look at some example, and then we're going back here to write a few more rules here. Okay, so in here, for this ones here, let's say evaluate the limit f x approach to, this is approach to the positive infinities, right? So positive infinity, that means my x value go this way, correct? So when you see these functions here, when the x getting closer and closer, which line it will going to close to? Is going to the negative 2 here, right? So that's why I would say the limit x approach to the positive infinity f of x. So do I reach your limits? Yes, the limit is -2. Okay, so the same things here. Take a look here. This is x approach to the negative infinity. So what means negative infinity? That means my value of x go this way here, correct? So now you look at this graph here, all right? So you look at this graph here, and then when I get closer and closer, what happens here? It's going to approach to what? X-axis, right? So what is the x-axis? That's the y equal to 0. So here I can write here, that's what we say, limit x approach to the negative infinity, f of x is equal to what? It's equal to 0 here. All right, that's just from the definition. Now let's take a look the second problem here. So the second problem here, this is x approach to the infinity. So if you put the x equal to the infinity, the square, if you square the infinity, it still will be infinities, right? Infinity minus 1 is infinity. So for here, you will have the situation is infinity over infinity. And this is very similar like the limit we did before when we have 0 over zeros, right? So this doesn't mean it's equal to 1 because when the infinity over infinity and 0 over 0 is, we don't know what is indeterminate forms here, right? So now I'm going to write a few like rules or we call the formulas will be able to help you to find the limits here. Okay, so here, let's try to write the first rules here, right? So this one is kind of like a kind of tricks here. So if you have functions, right? So if you have the functions limit, like an x approach to infinity, or you can say it's the positive infinity or negative infinity. If the function, you have two polynomial, all right, so the first one is the polynomial with nth degrees. That means is in here. Like I said, I use the positive infinity and the negative infinity to apply the same way. So what means the first, the nth power polynomial, that means you have an xn plus an minus 1 xn minus, okay, sorry, here. So here, okay. So that means x to the n minus 1 power, then da, 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 plus a1x plus a0s, right? Okay, so the same way, the denominator have another polynomial. So is here we have the am to the xn power plus am minus 1 to the x to the m minus 1 power, and the plus da, 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 da to the, to the a0. Well, I think maybe is like better, use the b instead of a, so we don't get confused. Okay, so this is the bm, and this is b to the m plus minus 1, and this is b0. Okay, so the first rule is to tell you here, right? So if you are trying to find the limit, for the two polynomial, as you can see, if you put x into the infinity, so what is those polynomial going to be? Let me erase this graph here so we can have a little bit more space to write. Okay, so as you can see here, right? So if you put the x approach to infinity, what happens here? The top will be infinity, the bottom will be infinities, right? So we come into these situations, infinity over infinity, and it's indeterminate. I don't know how to do it, all right? So the first rule is like we're dealing with the polynomials here. So the rule number 1 is here, okay? So the rule number 1 I will tell you, say, if the, okay, so we have situations here. If the n is equal to n, right? So that means if the exponents of n and n, they are equal. And because this is the polynomials, right? So the first term dominates the things. So if n and n, they are equal, That means the numerator and the denominator, they are going at the same rate when we approach to the infinities here. Because we are going to the same rate, so basically I can kind of, don't worry about the remaining terms here. I can only, I only need to focus on the first leading term, the one dominate that. So that means if n is equal to m, what's that mean? That means they are going to the infinity at the same rate. So then I can say, hey, my limit x approach to infinity, the Pn and the Pm, right? So that means then my rate, the limits will be an to the bm. See here, will just be the coefficient in front. Okay, so now let's take a look at the second ones here. So the second ones here is tell you if m greater than n. So if m greater than n, that means the denominator I have a higher power. So what's that mean? That means my denominator running faster than the numerator to the infinity. So I'm going to have something like the denominator, and this is kind of like some type of constant. We know if a denominator approaches to the infinity, the faster, and then what happens here? So the whole thing, the denominator gets bigger and bigger and bigger. So what is this limit going to be? So we said this is approach to the infinity. This is Pnx. This is Pmx. So what is this one going to be? It's going to be 0, right? It's similar because you can say, hey, if the m, then you can take out the 1. So they can cancel with the an. So now you have some constants over the infinity. Then it's going to become zeros here. Okay, so the rule number 3 is here. So how about if the m is less than m? If the m is less than m, that means what happens here? The top going a lot faster to the infinity than the bottoms, right? So if the less similar is kind of like you say, I have something go a lot faster to the infinity and the bottom is just a constant, right? So now here you said here, this is Pnx, Pm of x. Now what is this one going to be? It's going to be the infinities here, right? Because it's going to the infinity. Of course, when you do the real problems here, when we do the our examples here, you need to be careful about the negative sign, positive sign. And like I say here, I use the positive infinity to write out the rules. The negative infinity, it's the same. The only thing differences there is you need to be careful about the negative signs here. Okay, so let's try to practice these 3 rules here, right? Okay, so now the first one's here. Okay, so here, all right. So now in here, you take a look here, right? So this is the polynomial x squared minus 1, x squared plus 1. So remember, we look for the highest exponents. So the highest exponents here is 2, and the highest exponents on the denominator is 2. That means that these 2, doesn't matter it's minus 1, plus 1, I'm only care about the first term, right? Because the first term is the dominant term, like leading the other term. So minus 1 plus 1 does not make a difference when I go to infinity. So now in here, you see, both of them, right? So both of them go into the infinity the same rate, right? So that means I know from the rule number 1, I know both of them go to the same rate, and then will just be the constant in front. So x squared, what is the constant? Is 1, right? X squared is 1. So what is here? So it's 1 here. Okay. Okay, now let's skip the part B, and then let's take a look at the other ones. And then we'll go back to the part B here. Okay. So now the part C here, we say this is a polynomial. So here we say, oh, here this is a 3, this is a 3. So the dominant term is 3. So even in here, I have like a 2x squared plus 3, 7x, it doesn't matter, right? So because The x3 is the highest term. They run to the infinity the faster and is dominated the way they go to the infinity. So this is x cubed, x cubed. So they are the same. So what is the limit here? Will just be what? The constants in front. So what is the limit here? This is 5 3s here. Okay. And now let's take a look at this ones here. All right. So this ones here, we say the limit, be careful here. This one is going to the negative infinities, right? Okay, so in the negative infinity. So the first ones here, I need to take a look. So these ones here, the power, the exponents here, I did not write it. The 2x is really is a what? Is the first power, correct? So here, this is my first power. And then you take a look at the buttons here. The button, see here, I have, here is x squared. Remember, I don't care about the other term. Then you have a square root. So when you get the x squared, then you take the square roots. What happens here will be x. So it's the first term also, correct? So I know this one's here, be careful, right? So this one's here. Okay, so this term's here, right? So I know this is the first term also, the exponents is 1. Okay, so now let's see here, right? So we need to be careful, like I said, the positive and negative infinity doesn't make a difference, so we just need to be careful about the positive and negative sign. Okay, so in here, this is the x first power, and this one we know the exponent is first power also, but because of the square roots, so I know whatever come out here will be what? Has to be positive, correct? Because the x approaching to the negative infinity, you squared it will be positive when you come out the square roots. So the same things here, this one is going to the infinities, right? The negative infinity. So whatever comes out here will be what? It's negative. And because they have the same exponents. So we said, hey, by the rule number 1, if they have the same exponents here, so what is the limits here? The limits should be the constant in the front. So the constant for the top is 2, the bottom is 1. But because of the top is go to the negative infinity, the bottom is positive. So what is my final answer? Is negative 2, see here, right? So be very careful about the positive or negative. The reason why the bottom here is positive because the square root of the x square will be the x, but here is what is, is always positive come out the square roots, correct? Okay, good. Now let's take a look at let's skip this ones here, and then let's take a look at the other ones here. So this ones here, this is x cubed. So the highest power is x cubed. So what is here? This is the highest power is x squares, right? So what do we have here? So we say, hey, the top is running a lot faster than the bottoms here. Okay, so the top is a lot faster than the bottom. So that means what? What is the limit here? Limit here will be infinities, right? Because the top is go way faster because exponents here, this is the cube, this is the squares here. Okay, now let's take a look at back to here. So sine x. We had this type of the functions before. You know what we did before? We were using like this from our previous. We say that x approach to 0. We have a sine 1 over x, right? So we say x approach to 0, but if you put the 0 into here, the buttons here, the whole thing is going to be infinity, right? So we say it's an infinity. So we also know the sine, when they get into the, like when we talk about the going to the infinities, right? So the sine function, what going to happens here? So the sine functions here are going to be like when you go to the infinities, right? So you're going to go like this. So I don't know which one they're going to, because when infinity, so sign can jumping around, between the 1 and the negative ones here, right? So what is the limit here? This limit is do not exist, okay? All right, so now, because in here, I know this is between the 1 and the negative ones here, right? Okay, now let's take a look here. You say, okay, the limit x approach to infinity, the cosine x, you say, hey, cosine, we're jumping around. That's true, all right? But it doesn't matter the cosine jumping around, right? So we said, okay, cosine going to jumping around here, but the cosine is always between 1 and the negative ones, right? So now in here, I can write it this way here. So take a look here. I said the cosine x is always between 1 and the negative 1. Doesn't matter what is the value, correct? Okay, now I divided by x both sides. Okay, so now I divided by x here. So that means this is x and this is x. Now I'm taking the limits here. So I will say limit x approach to infinity. Negative 1x is less than equal to limit x approach to infinity, cosine x, and less than limit x approach to infinity, 1 over x here. Okay, take a look here. So when the x getting bigger and bigger, right? So when this one become very big, so what happened to this term going to become 2? We know a fraction, if your denominator get bigger and bigger, so what do we have here is 0. So the same way is here, when this getting bigger and bigger, what is going to have here? So here is 0. So I know my limit x approach to infinity, right? So I know my limit x approach to infinity, then this is a cosine x, and x will be bounded by 0 and 0. And remember what we called this? We called this is a squeeze, right? So by the squeeze theorem, we know the both end will be 0. So what is my final answers here? My final answer will be what? Will be zeros here. Correct? Okay, that's what we call it is the squeeze series here. All right. Because the cosine, they do have boundaries here. So now let's go back to here. We said, hey, let's take a look, the polynomial. Then the rule number 1 here, we take a look, said by applying the squeeze theory to see if the squeeze theory will help us if for some reason I don't have, the polynomial over polynomials here, okay? So then I'm going to write another rules here. This is the one we're going to take a look at our next examples here, right? We did these 3 examples. So now let's take a look here. So we said, all right, so now in here, I have limit x approach to infinity, the square root of x plus 1 and minus the square root of x plus x here. So when you put the infinity here, so infinity plus 1 is infinity. So what I have here, I have infinity minus infinity, right? So I know the infinity minus infinity is indeterminate. I don't know, right? So I don't know. This is we cannot say is equal to 0, right? We don't know, right? So how about if you have the infinity minus infinity situations here, what you need to do here, right? And then in here, this is the kind of we said here, how about situations, right? If you have infinity minus infinity. So how do you do it? And the one way you can do it is maybe, doing by multiplying, conjugate. We used this skill before, right? So let's try to do this one more time here. Okay, so let's take a look. This is infinity minus infinities, right? So I want to get rid of that. So the way we do that, we say, okay, so this is a limit x approach to infinities, right? So this is by functions here. This is x plus 1 minus x here. So what I need to do, hey, let's try to times the conjugate, right? So remember, what is the conjugate? The conjugate is just you change the plus sign to the minus sign or minus sign to the plus sign here. And you cannot just times it. So I need to do this. So basically I'm multiplying 1. So I did not change anything, right? Also, do you remember? Okay, so now here, this is limit x approach to infinity. So the denominator will become x plus 1 plus x, right? Okay, so x plus 1 plus square root of x. So the top, remember what formula we use? We say this is one very popular factoring formula. Is a minus b times a plus b. So do we remember what is this from our algebra year? So it's a square minus b squares, right? Okay, so now in here, this is a squares, right? Minus b square. So this is my a, this is my what? B's, right? So this is a, this is b's here, right? So a minus b times a plus b. So what is that? Is a square. So x plus 1 square roots, your square is what? Is x plus 1 minus x. All right. So now, okay. So now you see here, okay. So now I can cancels, right? Okay, so now let's see here. This will give me limit x approach to infinity. So I have what here is 1, and then this is x plus 1 plus square root of x. Okay, so now I'm try again. So when you put the x equal to the infinity over here, so what is this one going to be? This is going to be infinity. This is going to be infinity. So I have something like very similar to kind of like infinity plus infinities, right? So this ones here will be something very similar, like okay, what happens here? Okay, so it's kind of similar like infinity plus infinity. So is infinity plus infinity is like defined? Yes, so it will be similar to the infinity. So if you have a constant, right? If you have a constant over infinity, when the bottom get to larger and larger, so what is this one here? This one will be what? Will be 0, right? Because this is a constant, right? So now your denominator getting bigger and bigger and bigger. So we know from the, the algebra, I know for fraction, if the denominator get bigger and bigger, then this will become bigger. So number 4 is here. They said if a is greater than 0, is sometimes, always, or never. So to the ax is become to infinity. That means if you let your, so in here, take a look here. That means if you let your exponents getting bigger and bigger, is that going to the infinity? See here? Well, this one's here, the answer is sometimes here. Why is it sometimes here? Okay, so if a is greater than 1, so think about it. You take exponents higher and higher. So for example, I have a 3.5. So I take the x exponents. Then x getting bigger and bigger. So what happened here? This one going to the infinity. That's true. But if I have a less than 1, say here, if I have 1/2, then when the x going to the infinity, what this one going to approach to? Will approach to 0s, right? Because then your denominator going to get bigger and bigger. Then so this is like when x equal to 1 is 1/2, x equal to 2 is 1/4, x equal to 3 is 1/8, correct? So that's why this one we say is sometimes here. Okay, and so now we are going to introduce another terminologies we call the horizontal asymptote. So what is the horizontal asymptote? So the horizontal asymptote, so it's a function, it's the lines, right? So it's a line, just like a vertical asymptote we did before. This line is y is equal to some numbers here, okay? And so this line satisfies, so such that, like we talk about, this is when the limit x approach to infinity, f of x equal to L, or limit x approach to infinity. I'm sorry, here, this is x approach to negative infinities, right? Okay, so you go to the both end, the negative infinity, f of x equal to L. So the limits here, the L, the limits here, right? So it's the line y equal to L. This is what we call the asymptote. So the horizontal asymptote is the x going to the infinities, right? So here, make sure you cannot remember. So the horizontal asymptote is x going to the infinity or x going to the negative infinities, right? So when we talk about the vertical asymptote, so let's try to refresh our memory. Okay, so the vertical asymptote is like if you have a functions, right? F of x is equal to the px qx here, right? So what is the vertical asymptote? So the vertical asymptote is all the x value, the qx equal to 0. That means your denominator is not defined. Okay, so now let's take a look at the horizontal asymptote. You can have several different situations here. Let me show you the graph. I always like to use the graph, and the graph maybe is easier for you to see, right? Okay, so here, the first situations here, we say, okay, so this is my, so then like in here, we say, this is my line. So this is the else here. So this is y equal to L. So this is the what? So this is the horizontal asymptote, because when the f of functions here go, when the x go into the infinity, this curve going to get closer and closer to that lines here, right? Okay, now let's take a look at another ones here. Okay, so the another ones here, for example, I can have some graph here. Okay, so for these ones here, okay, so here will be my y equal to L. So this is my, so this is my horizontal asymptote, and this one here is x approach to what? To negative infinity, right? So if you write this type of asymptote is limit x approach to the positive infinity, fx equal to L. And this one, because x is going this direction, so you will say limit x approach to what? Negative infinity, f of x equal to L. So the same way, let's take a look here. Okay, let's take a look at other situations here. Okay, so in here, if this is my else here, right? So then my function can go like this. All right. So like one end go to the, so they both, right? So this leg go into the L, and this leg go into the else, right? So how do we write this? We say this is a limit x approach to infinity, f of x equal to L, and limit x approach to infinity, f of x equal to the, here, I need to be careful. So this is when the, to the negative infinities, right? So this is negative infinity. So don't forget this negative signs here, right? That is what is the, we call this the horizontal asymptote. So from the previous lecture, we know the vertical. So now we know what is the horizontal. So horizontal, make sure is when your x getting to the infinity. It's getting the bigger and the bigger. All right, so let's take a look. find the horizontal asymptote. So remember, horizontal asymptote is y equal to some numbers, right? So what is the horizontal asymptote? Here is this one, right? So the horizontal asymptote is y equal to what? -2. So still remember, what is this one here? This is, we call this what? The verticals, right? So this is the vertical asymptote. So what is the vertical asymptote? This one here is x equal to 2. That means your function is going to get closer and closer. And then also for the horizontal asymptote here, for if you look this way, it's going to closer and closer to the x-axis. So I have another horizontal asymptote, it's y equal to 0, right? So I have 2 horizontal asymptote and 1 vertical asymptotes here. Okay, so now let's take a look here. This one is a very good problem. So let's say find the horizontal asymptote for the f of x. So let's see here. We know the definition for the horizontal asymptote is x approach to infinity, right? So the x approach to infinity, this is x, this is the absolute value of the x minus 1. So if the limit approach to x approach to infinity is positive, so this is x. So if it's a positive, what happened to the absolute value of x? How do you break it? It will just be the positives, right? So it's -1. So now they both here, look here, this is the first exponent, they have the same exponent. So what is the limit here? Limit is 1. Good? All right. So now let's take a look at the limit x approach to the negative infinity. So this is x minus 1. So this is the limit x approach to the negative infinity. Okay, take a look here, right? So when the x approach, so this one is x here, but this is the absolute value. So if it's negative absolute value, what do you need to do when you break the absolute value? You need to add the negative sign in front, right? So now they still both have the first exponent. So that means from the polynomial rules, I know what is here is -1. So how many horizontal asymptotes I have? I have 2, right? So I have y equal to 1 and y equal to -1, all right? Be careful. So in here, this is a kind of a refresh your memory. So if how do you break the absolute value of x? So it will be equal to x if x is greater than or equal to 0, right? So we remember if you break it, if you put a negative sign to that, if x is less than 0, correct? Okay, now let's take a look here. The next one here is find the horizontal asymptote. Okay, so from the horizontal asymptotes here, let's see what we have here. So remember the horizontal asymptote, it will be like a limit x approach to infinity, right? Or negative infinity. So this is 1 minus cosine x and x. So we know when the x approach to the infinity, the cosine x is going to jumping around like that. So we say, well, what can we do? So remember, so for this situation, let's try to see the squeeze theory will work, all right? So let's start with cosine x. Cosine x is always between 1 and -1, correct? Now you have negative cosine x. So I add a negative sign and I switch, right? Okay, now I have 1 minus. So this is 1 minus cosine x. So this will be 0. This is 2. All right, so now I have x here divided by x divided by x here. Let's just switch it, make it the signs a little better. So this is 1 cosine x, x. So this less than 2x, and this is less than what? This is less than 0 to the x, right? The 0 to the x is always 0. So now this one's here, I can say limit x approach to infinities here, right? So this one's, I can put the limit on all the 3 sides here. Okay, So I can put this all the three sides. So this is the limit x approach to infinity. And let's still keep it. So just in case you got confused. So this is the limit x approach to the infinity, 1 minus cosine x less than limit x approach to the infinity, 2x, right? Okay, so what happens here? So when x getting the bigger and the bigger, so what is this number going to become to? The 2 over infinity, right? So this will be 0. So this is x get bigger and bigger. So what is this one? It's going to is the zeros here. So I know this one's here. So now this one going to be squeezed to what? Squeezed to the zeros here. Correct? Okay, so now let's take a look. How about if I have the negative infinity? Okay, so let's see here. So let's see the squeeze theorem still work or not. So if I have a negative infinity, negative infinity, negative infinity. So the same way when these ones here go to negative infinity, this still is 0. This still is 0. So now I know the limit x approach to the negative infinity, 1 minus cosine x, x still going by the squeeze theory, still going to be 0. So how many horizontal asymptote I have? I only have one, right? Is y equal to 0. That means it's the x-axis. All right. Okay, so now number 8, this is a good review. We said find the asymptotes here, right? So the first ones here, we know we have vertical asymptote and horizontal asymptote. Okay, so let's find the horizontal asymptote. So it's x approach to infinity, x squared. You see here, right? So the x and the x squares here. And so because this is the first power, right? So x1, and this is the second power. Oh, that means the bottom is going a lot faster than the top. That means my denominator going to get bigger. So what happens here? This is 0. See here. All right, so now let's take a look at limit x approach to the negative infinity. So this is x squared minus 1. So even this is negative infinity, my bottom still go a lot faster, right? Because bottom is just like a square and the top is just the first power. So what is here? So it's 0, see here, right? So how many horizontal asymptote I have? I only have 1. So my 1 is y equal to 0. Okay, so now let's take a look at the vertical asymptote. If you still remember, the vertical asymptote is the one, my denominator will become to 0. So if I factor this, this will give me x minus 1, x plus 1, right? So we know the vertical asymptote is when your denominator equal to 0. So that means x minus 1 equal to 0 and x plus 1 equal to 0. So what is so x equal to 1 or x equal to what? Equal to negative 1. So both of this, those are what? This is my vertical asymptotes here, right? So for this function, I have 2 vertical asymptotes and 1 horizontal asymptotes. Okay, that's it. All right, so that is how do we find the limits instead of x approach to a constant like 8, right? So like we wrote here instead of x approach to a. So now how about when x go into the positive infinity or negative infinities here? So those are the few rules will help us. Is it better? You know, it's best if they have a polynomial over polynomial, then it's pretty easy, right? So for the different situation, sometimes you might need to manipulate your function. Sometimes you might need to do some conjugate or multiply the functions, and like the older kind of the techniques we talk about in the previous lecture series, the lectures there, all right? Okay, that's it. That is for the list sections here. How do I find the limit when the x approach to the infinity? And that's what is we call that's how do we define the horizontal asymptote is when x go to the positive infinity and or go to the negative infinities, right? Okay, that's it. And nice to talk to you. And the next section, we finally be able to kind of start to define what is our derivative by using the limit definitions here. Looking forward to talk to you for our next lecture topics here. Okay, bye. Have a good day. Okay.